have the same teacher from the first one?
My first teacher, she retired. And she was my advisor too.
What's her name?
Okay, guys. How we doing? Have some fun today? Let's have some fun this evening. Let's finish up acid base. We'll start alkane conformations. Can someone close the door? Thank you, Larry. We've got a couple minutes maybe for questions. There we go, right there. Go ahead with a question while I'm getting this set up. Anybody? Question?
Can you explain the very first question on the acid base warm-up?
Acid base warm-up.
Yeah.
That's what we need. Acid base warm-up. Which alkoxide is the most stable? I think that one might have been on the notes page, right? Didn't we do that?
Yes.
Document canvas. Thank you very much. You did that one, yeah? Which one's most stable? Who says this one chlorine?
Yeah.
Who says this with the fluorine? Good, you would be right. Why did you think this one?
Look at the size of the chlorine.
Because what?
The size of the chlorine relative to the chlorine.
Okay, what did we say about the size though? You only consider that
And the
charge is on that atom. Charge here is not on the chlorine or the fluorine. The only thing here is the halogen is just it's inductively pulling. Which pulls more? F or Cl? Yep.
Okay.
All right. You're right there. That's it. Question
Can you also go on to number 9?
number 9. We'll do that one in class. We haven't quite got there. That's the last page. Kingsley?
So you have number 5 in the workbook.
I can't hear you, Kingsley.
Number 5 in the workbook, you have sodium acetate.
Which page in the workbook?
Page 8, number 5.
Page 8, number 5.
Yeah. So
You tried. Tried it.
Page 5.
No, you have
you have one acid that can stabilize its charge on 3 separate carbons, and on the nitrogen, or and then you have sodium acetate. My question is, why does sodium acetate have a much lower pKa when you have charge stabilized at 3 different sites and stabilized from the nitrogen? And that's what it is.
Sodium acetate. Why are you quoting a pK for sodium acetate?
Because you said to get the pK of sodium acetate to compare the acids.
But I didn't say you're getting pK for sodium acetate. You need the pK for the other acid in this equilibrium. What's the other acid? You got to show the right side. There's an acid on this side, and there's going to be an acid on the other side of the equilibrium arrows.
Yeah, so once that undergoes dissociation, you have this, you have the sodium gone, basically. This acid down here. This, they don't go one to the other oxygen.
Okay, let's do this one. Let's do number 5 on page 8. Well, I mean, we're in the workbook. The answers are in the back.
Yeah.
We don't really need to do it. So what's your question?
Why is the pK for sodium acetate much lower?
The pK for sodium acetate is irrelevant. Well, you're referring to the pK of acetic acid.
Yes.
pK of acetic acid is about 5. pK of the other thing is 8. Which is favored, 5 or 8?
No, but why? It seems
Oh, you want to know why it's 5?
Yeah, since counterintuitive, because resonance was stable.
Okay, I understand your question now. Okay. Okay. Because the structure there, okay, we're now officially started, guys. Okay. What's the acid-base reaction? Well, you got to identify what's the acid, what's the base. Okay. Well, I gave you a pKa here. That sort of maybe gives you, even if it's not there, I still expect you to know which one's the acid. Okay. Well, sodium acetate. First of all, this is organic chemistry. This is an ion. That's a plus and that's a minus. Okay. And anions are typically bases. We said that, right? Now, there's exceptions. They may not be strong bases. That's going to be your base. So this is the acid. If this is the acid, which H of this is most acidic? Alcohol. The one on the oxygen, because you'd rather make an anion there than carbon. Okay? So that's a bond there. Acetate. Everybody knows acetate, right? Acetate, these electrons take the H, these electrons move on to oxygen, and you get oxygen now having 3 lone pairs, that's a minus charge. You also have the nitro group, plus, now there's an H bonded there. That's acetic acid, its pK is 5, this one's 8, which side's favored? I hope I said it right earlier. It's this side's favored, right? Yeah. Yeah. Favored by how much? By 10 to the 3. Is that right? What's that, 1,000? At equilibrium, you have 1,000 of these and only one that's in the anion form. Okay? The question is, why is this not more acidic than this? You think that's more, you want this to be more acidic. Why, Kingsley?
You could actually, like, the charge is stabilized at 3 different carbons.
Okay.
You put on the nitrogen.
Lots of charge delocalization.
Yeah.
Lots of resin. Yeah. But when you start delocalizing the charge, you're going to move it on to what other atom?
Carbon.
Carbon and carbon and carbon. In this guy, if you do delocalize it, you'll delocalize it onto what? Oxygen. Here you put it on 2 oxygens. Here it's only on 1 oxygen, the other carbon.
Okay, and continuing that like resin structure, can you like add 2 more pairs of nitrogen? Because nitrogen.
You can actually, you can actually delocalize this into the, yeah.
But it's not as strong as oxygen. In this case, it's not as
It's complex. First off, trust the pKa's. You start disrupting the benzene ring. When you start disrupting the benzene ring, it's just not as acidic. I talk about this specifically in Organic 2. A lot of times students think because you can draw more resonance structures here, it should be more stable. Not always. It depends on a couple more things. What type of atoms are you putting the charge on? Okay? It's very good to question this. It took me a while to figure out what you were asking. It's actually a good question. Right now, we don't really need to know this, okay? Organic 2, I go over that again, and I expect you to really know what I just talked about. Okay. Let's get to topics at hand. We got that there. That's the right hand. No, that's the work. Under there. I think we're ready to start on this page here. Henderson-Hasselbalch equation. How do things exist at certain pH? Okay, neutral form or ionized form, essentially. Henderson-Hasselbalch is an equation that can tell you that. In biochem, you used to derive that. I don't know if you still do in biochem. Basically, it says that pH equals pKa plus log of B over A. B is the basic species. A is the acidic species. Okay? Because of all that, you can sum that up into, right here, in summary. If pH is greater than pKa, the basic species will predominate. It's not going to be just all the basic species, but you'll have predominantly the basic species. If pH is less than pKa, the acidic species will predominate. What is the basic species versus the acidic species? The acidic species has the proton. It's ready to act as an acid. The basic species does not. It has already given up the proton. That's the A versus B. Do not confuse it with charge. Students all the time say that's negative and so it's the basic. No. A and B is determined, does it have the proton or does it not? That's it. So let's look at an example. We'll see an example of that and then the summary statement. Here's acetic acid. We just saw it in the previous question. There you go, acetic acid. How will it exist at pH of 7, which is the pH of blood? You've got acetic acid in your blood, how will it exist? Well, how could it possibly? What are the choices? It could be the neutral form or the ionized form. Well, that's an acid, and acids give up the H's and become negative, right? Okay, you got to know that. You got to be able to draw the. Okay, which form has the H? Duh, that one right there, yeah. All right, so that's the acidic species. That one don't got the H. That's the basic species. Okay, so those are your species. Now, you got to know a pKa. What do you have to know up there? There's 3 variables. You got to know 2 of the things. If you know 2 of the variables, you can get the other. Usually you'll know pH and pKa in what I give you. pH is 7. What's the pKa? 5. Okay? So one's 5, one's 7. Which one's going to predominate? But it's already said over here, right? Let's see. Don't mix up which is which. A lot of times students say, well, 7 is higher than 5. Other times students say 5 is lower than 7. You got to know which way you're kind of comparing. Importantly, which one of these can vary, 7 or 5, in this, the pKa or the pH? pH can vary. pKa for acetic acid will never vary. The thing that can vary is it on the high side or low side of the pKa? 7 is on the high side. Right? Okay. High side. Now is the high side the basic side or the acidic side? Basic. Higher the pH, more basic. The high side is basic. Your basic species is going to predominate. Because, in this scenario, the pH is greater than the pKa, isn't it? 7 is greater than 5. 7 is greater than 5, B will predominate. What is B? Right here. At pH of 7, acetic acid will mainly be in this form. Basic form. But I see a lot of students mess this up because they say 5 is lower than 7 and we're on the acidic side. No, you're comparing the wrong number. The thing that can vary, where does it sit compared? The thing that can vary is on the high side of the constant. Maybe it's on the low side. If the pH was 3, it'd be on the low side of the constant. And if it was a pH of 3, which side would be favored? The A form, the acidic form. Okay, you need to read this. Hopefully you've already read it. And what I said made a little bit more sense than seeing it the first time. At the bottom, I think that's just kind of a little miscellaneous note, nothing I'm going to go over here. A little bit of things about charges. etc. What we can do, I think on the warm-up there's one that, did somebody ask about this one? Yeah. That's on the warm-up page, down at the bottom, number 9, show how the following amino acid, serine, will exist at pH of 7. That happens to be the same pH in our example. I could have said pH of 12 or 1. Okay? What else we need to know to do this? What's the pKa of that right there? 3.5. That's about 5. That's the carboxylic acid. What's the pKa of that? What functional group is that? Alcohol. Alcohol is the same pKa of water. What is water? 16. This is an amine. It's an sp3 nitrogen. Anybody have that? I love this. Somebody's already tried to work this. Somebody, 10. I got it. 10. But that refers actually to what? Conjugate acid. It's actually the conjugate acid. Because amines are not acids, amines are bases. Okay? Do that. Now, we got 3 different ones to get the right form. How about this one? How is this going to exist at pH of 7? And acidic species or basic species? Basic. 7 is higher than 5. It's on the basic side. What's the basic species? You got to be able to draw it. Proton on or off? Off. What is it going to look like? That. Because when a carboxylic acid acts as an acid, it becomes this. Okay? Let's go down here. It's going to be down here. 16. Is this going to be in the acidic or basic form? 16 is on the high side of 7. But that's not the right way to look at it. We want to say the thing that can vary. That's the thing that can vary. What side is it on compared to the constant?
Low.
Low side. So which is going to predominate, A or B?
A.
Okay. So what is A going to look like?
OH.
Proton on. And if the proton's on, what's it going to look like?
OH.
OH. Now a lot of students will put another H here. Why is that not right? Because you got to know what your 2 forms are. What is the other possible form here? O minus. It's either that or O minus. These are your 2 choices. Not putting an H on. If an H was put on, that would be a different pKa. You got to know what your pKa refers to. pKa refers to that H. Only here does it refer to a undrawn H. Okay? Basically, that's going to exist just like over here. This is the B. That's the B form. What form is this? A form. Okay. How is this going to exist? Let's see. It's at 10. 7's constant. No, this is constant. We're at 7. Or are we on the? Somebody tell me. Is this A or B? Yeah. It's going to be A because we're on the low side of the constant. Low side of the constant A. What does the acidic form look like? Proton on. Okay, what does proton on look like? I see protons on. NH3. And NH3 is going to have a positive. Because what does 10 refer to? 10 refers to an equilibrium. It's between this and what? Conjugate acid. What does the conjugate acid look like? NH3 plus. Of the 2, which one's the acidic species? The one with the proton. That's got the proton, the extra proton. This does not have the extra proton. That's the B form. We decided the A form predominates. That's why I drew the A form here, A form here. But for that guy, the B form predominates. That's using your Henderson-Hasselbalch. Question?
Are the PKAs of the functional groups given to us?
Some may be. These probably not. No. Okay. You need to know carboxylic acid. Let's go ahead and say it. This is your amino acid. Amino acid. You need to know these pKa's right here. Yeah, you pretty much need to know these here. Let's go ahead and say that. Alcohols are like water, 16. So that's Henderson-Hasselbalch. Okay. We'll use that idea right there a lot in red too. Remember, we're building foundation here. Okay, the last couple. Any questions about the last couple pages? A couple of examples, sort of a summary page, which I hope is useful. Any questions about anything in this acid-base handout? Other warm-up questions? Other questions about the acid-base handout? Surprise. Okay, let's move on to the alkanes, cycloalkanes. Yes. Alkanes, cycloalkanes, you got this handout, the warm-up page has the pills there. So we're going to move on and talk about, start talking about individual classes of compounds and their reactivity, unique features of them, their properties, unique, the basic introduction concepts related to different classes of compounds. Alkanes, cycloalkanes, you see them everywhere. Questions there? Nomenclature, okay? You need to know how to name these. And so I put this video there online, went over these. I hope the video quality was okay. I looked at a little bit of it, and sometimes my quality was kind of Zoom or something. But you did have the handout there in front of you, and so if you couldn't see it on the video, you had it right here on your paper. Okay? If there's ever any issues like that, please just tell me. Otherwise, I think they're fine for everybody. I did not cover this one here. Let's name this guy here, right? Did I leave one unnamed? Okay. But before we name that, any questions about nomenclature that was on that video? Question?
So I just got a little bit confused. So if you have, let's say if it was like one, you always go in alphabetical order regardless of the number. So if like you hit like 2 fluoro and like 1 methyl, 2 fluoro would go first.
When you list your substituents,
Okay.
they're listed alphabetically,
Okay.
not by number. I actually had to mark that out on the handout.
Okay.
I just got it wrong when I was doing it.
Okay.
Yeah. Other questions about nomenclature? So let's name this guy over here. Anybody got this guy named? Everyone tell me what's the... Okay, let me write that down. 1-methyl propyl.
6 propyl
I'm sorry.
6 propyl decane.
6
Propyl decane.
propyl
Decane.
decane. Is that complete?
Yes.
Anybody want to quickly say something else? Did you get something else?
Yeah, can that methylpropyl be sec-butyl?
Perhaps, that's a common name. Okay. On quizzes or tests, I may, typically IUPAC is always acceptable. I may say common names can be used, or I may say only IUPAC. Okay. So let's look at it. Let's see if this is right. Longest continuous chain, 1, 2, 3, 4. Not that one. Let's start over here. 1, 2, 3, 4, 5, 6, 7. No. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's the 10. Is there another way to get 10? 1, 2, 3, 4, 5, 6, 7, 8. I don't think so, and it happens to be right through there. I don't know if this one was also right through there, was it?
No.
You know, sometimes it may be sort of up through here or something. Hopefully my example did show some variation. If that's the only decane, then that's it. Okay? If there were two different decanes, how would you choose? The one with the most substituents coming off of that. Okay. This has how many substituents coming off? 2. There they are. But we don't have to, okay. What is this substituent? 1, 2, 3. That's a straight chain just called propyl. Okay? And that apparently is where you got that from. What's going to be the 1 in? It's either going to be over here or over here. If this is 1, that's 2, 3, 4, 5, 6. Let's write that down. 5, 6 for your 2 substituents. Over here it'd be 1, 2, 3, 4. Oh, both 5, 6. How are we going to decide between both 5 and 6? Yeah, then go alphabetical. Well, we got to name the substituents first. This is propyl. Already written in the name. What do you want to call this? This is a what? That looks like a complex sub because it's 1, 2, 3 or 1, 2. Well, the longer is the parent. The first carbon is 1, 2, 3. The first carbon coming off the parent is 1. The 1 carbon has something. What's on the 1 carbon? A methyl. So indeed, that is a 1-methyl propyl. So that's where you got that from. So here's our 2 substituents. I could have written them up there. This is M, that's P. You just put the M first, and so you want to make the 5 be the M. So that'd be 1 here, 2, 3, 4, 5, 6. So at the 5 we have a 1-methyl propyl, that's a complex sub. At the 6 we have a propyl, and then it's on the decane. How we do? Question?
If you use the common names, the isopropyl and all that, how would the alphabetical rules apply to that?
Okay. Can we do a common name here for this guy? Yeah, that is a sec-butyl. For the sec-butyl, the sec is not counted. It'd be B. Anytime you have like a hyphen, it's not counted. B and P, so it would still be 5. Because B would still come before P. Now if this made it switch, then that's where probably you would just stick to IUPAC. Question?
So for the common names, like, I just apply to IUPAC, so it's, in terms of alphabetical, so like the sec-butyl, the first letter you consider is butyl, right, the B, not the S. For IUPAC names, is there ever a time where you don't consider like the first, if you have like dimethyl, so N is considered like the first letter,
Yes. Trimethyl would be M.
Okay.
Isopropyl would be I.
Okay.
I think that about covers it all. I can get into more complex, but for us, I think that's all we need. You go to the library, there's a book about it called IUPAC nomenclature. It used to be always blue. People used to probably blue book, put out by IUPAC. They'll name all types of things, crazy rings, crazy compounds. Okay, this is really page 1 of that book. If you ever have a chance to look at it, those people take their naming seriously. Okay? They'll come knock on your door if you start naming things wrong. Everything else was there. Flip side. Questions about nomenclature? For the prefixes, it was methane, methyl through 10 decane. Oh yeah, there's one over here I didn't name, right? This guy with the iodine. And basically, this is where the cutoff is for the test. The rest is sort of just so you can start getting an idea of some more functional group naming. For the test, it's going to be plain alkanes, including halides. Halides is substituents. I think we named those. This guy here, right? Longest continuous chain. 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3. I see 5. Either way you go, there or there, it's the same thing. I thought somebody said hexane.
Pentane.
Nobody said hexane? Okay. It looks like pentane to me. Is there another pentane possible?
Yeah.
I mean, starting here? That's really not a different. I mean, if you started there, you get the same exact name. 1, 2, 3. I don't know why, but it seemed like this example had another one. How? Here? 1, 2, 3, 4, 5. That's the same thing as what I have circled because of symmetry. Yeah. Okay, I think that's it. Anybody see something, shout out. So we got a pentane. What's on our pentane? Iodo, chloro, and the methyl. Okay? What do you want the one position to be? Left end or right end?
Left.
The left, because iodine is first in alphabet.
Over here you'd have 2, 3, 4. 2, 3, 4. Over here you'd have 2, 3, 4. So again, we're going to have to look at alphabetical. Iodine or methyl? Iodine. Iodine is going to be, went out alphabetical, so it's going to be 1, 2, 3, 4, 5. Now we can list our substituents alphabetical. 3 chloro, 2 iodo, 4 methyl pentane. Did we get it right? Anybody?
So I noticed that you capitalized the C. Is that what is the role of capitalization?
I sort of go with the first letter capitalized, like a name, proper name. But if you were writing a paragraph, I probably would not capitalize the C. So there's really, it's not important for us. But another question?
No.
Okay, guys, so that was nomenclature of alkanes. Is it work okay to put that on the video and then do some quick examples? What that's going to allow us to do is talk about, have more time for the sort of the more in-depth stuff. And I'm probably going to put nomenclature for for future test also online. Okay. Couple more things about structural. One is condensed formulas and structures. I've sort of maybe have mentioned this before. Let's look at it in detail here. Sometimes you'll see structures written like this. Well, that's really not a structure. That's somewhere between pure formula and structure. These are called kind of condensed structures, where it's condensed down into something that maybe you can type out. But it's still, they're still showing you some structural information, and not just showing this like C8H12O2, like formula. But this is pretty darn common, especially when you standardize MCATs and PCATs. You see lots of condensed stuff. Okay? You need to get used to these. So, you'll see brackets and stuff, and then you'll see functional groups that are condensed down. So I did the first one for us. Put together a structure here. Okay, you got two CH3s. That's what it said. There's two of those. Well, they just bonded together? No, that's all you would have. Basically, you got a carbon with two methyls. Let's draw it out with a C instead of a line. Carbon with two methyls. Okay. Now this carbon has what on it? There's an H on it that's there. But then it's apparently also to another carbon. And that carbon has what on it? Two H's and then a what? Then an OH. Okay? That's what it is. And if we turn this into plain line bond formula, it's that what I showed over there. We got a carbon with two methyls, CH2OH. Kind of see that there? So let's do the next two. Why don't you guys on the right here, my right, do that one. And you guys on my left do this one. Draw out a line bond structure for it. Let's see how we do. Okay, what we got here? We got three CH3s. What are they all bonded to? Only the carbon. So I'm going to do straight to line bond. I'm just going to put kind of a dot there. There's a carbon, and there's three CH3s there. So let's do boom, boom, boom. CH3, CH3, CH3. Well, that is a CH3 right on the end. It's a carbon, and then it's got three H's because three bonds got drawn in. So there's a carbon with three. And that carbon's bonded to, well, another carbon. What's on that carbon?
Two CH3s.
It looks like two CH3s. You can draw those any way you want. By the way, we're fixing to talk about that, conformations. Then what? Now it's like a CH2. I'm not going to draw the H's in. Now what is this bonded to? Another carbon. What is it bonded to?
Alcohol.
That's not it.
It's double bonded with oxygen.
Aldehyde.
Aldehyde. And the H is actually on the carbon. Because if you drew that as an alcohol, there's the CH2. If I came over and put a carbon with an OH, well, that carbon only has 2 bonds. Where are the other 2 H's? I mean, we're showing all the H's here. Okay, that is not omitting the H's. All the H's are shown. So, if you want, you wouldn't have an octet. No, what you have to know is the CHO is condensed version of what? CHO is your condensed version of your aldehyde group. That's how it's condensed down. Okay, question?
Will a formula ever be written that contains an alcohol that isn't written OH?
I'm not quite sure. Look at this here. We actually did this on day 1. CH4O. That's just pure formula. A lot of times this is written as CH3OH. It's the same formula. Why do people write it like this? Because here it tells you a little bit of information. And this clearly, now you know it's methanol, 1 carbon alcohol. You might see an alcohol like that. I would never draw methanol like that. Anytime I show methanol, I'll draw it like this. But yeah, I mean, that has an OH. I think it has to. Maybe wrong, but I don't know if there's a constitutional isomer or not. Okay. So, you got to be on the lookout for some condensed, common condensed things. That's your aldehyde group. Back there.
How will carboxylic acid be
Right that. You guys over there already seen that? Carboxylic acid is CO2H, or sometimes it's COOH, and they write out both O's. Who is they? Whoever did it. IUPAC. So 2 different ways for that. So let's get over here. Somebody over here got it? Well, it's hard to tell me what you got, so let me just do it. Let's see, I see a CH3. Okay, CH3, what is it connected to? A carbon, what's on that carbon? 2 methyls, and then what do we have? We have a carboxylic acid. So let's just do that. How we do? Okay, that's what it is. This is condensed for your carboxylic acid. On the functional group page, did they show condensed versions? Functional group handout? Let me just look real quick. Functional groups. They say COOH for carboxy. They don't. Yeah, see, I wish they would show condensed version for like aldehyde. I wish they would have showed CHO. Very common for aldehyde. Look for those in your textbook, okay? Practice your condensed.
Professor,
Yes.
for the third condensed formula, that right there, is it possible to write CH3 like the second one did, and then a C for the CO2?
Make this 3?
Well, like it started off like the second one, right above there, right? And then use 2 C's and then another 2 A's.
You want CH3?
Put the initial C after that.
Okay,
And then it'd be another, I believe another C and then OH.
like that?
Right.
Well, let's see what that would be. It looks like you got a carbon with 3 methyls. And then you got a carboxylic acid.
I mean, it is the same.
Carbon with,
It's the same thing.
Yeah.
that is that.
Yes.
It's also the same thing. Isn't it also the same thing when it raised it? What? It's the same thing. So I think the answer is that's another way to show the same thing. I think you're right.
There's no convention then that dictates, one form over the other one, they both do the same.
I don't see anyone that's preferred. I probably just drew these out and then as examples. I could have drawn that one out, but I just gave you a variation. You should be able to do them both. But they both do lead to the same thing, it looks like. Okay, classification of carbons. Primary, secondary, tertiary. This is just like with amines. Okay? A primary amine, the nitrogen is bonded to how many carbon groups? Primary amine, the nitrogen is bonded to 1 carbon group. Okay? Thus, we can use terminology like a primary carbon is bonded to how many carbon groups? It's the same thing, 1. It's just with amines, it's much more standardized to use that. With alkanes, it's more of a more variation, and so we didn't cover it back over there. We're going to cover it here.
What's the difference between a quaternary carbon and a chiral carbon?
Usually chiral carbons are quaternary, but not all quaternary carbons are chiral. All right. Did that answer it? I think it did. But it's kind of like, you know, you hear that with other things. Okay, look at this formula here. This carbon right here is a primary carbon. Why? That means it's bonded to 1 other carbon. Is it? Yeah. All right. Primary carbon. Don't look there. This carbon's bonded to how many more carbons? How many carbons? Bonded that one, that one, that one. So that carbon is tertiary. Okay? That carbon is bonded to how many carbons? 4. So it is 4. All right, now we're snowballing. Okay. That's what that is. Now you do have to be careful because, like even on the video, I called this a what do you call that group there? Common name for that group. Sec-butyl. And I said it's sec because why? Because the first carbon is secondary. It's bonded to 2 carbons. See, that's assuming that's not a carbon then over here. It's a chlorine. If it's a chlorine, that's clearly a secondary carbon. Now, if this is a carbon over here like this, somebody still may call that a sec-butyl. But it's officially not. It's officially a tertiary carbon. So you just sometimes have to be open to, okay, they're not using it correctly. Sometimes this terminology is not used strictly correctly. But guess what? I'll never trick you or anything. Right there is what we'll be accountable for.
Is that short?
Question. All right. So it's just like amines and amines. There's examples there. Now you can also use this terminology for describing the H's. The H's here on this carbon. Those H's are called secondary CHs because they're on a secondary carbon. Those H's are called what?
Primary.
Yeah, the 3 H's there are primary CHs. They're on a primary carbon. How many primary CHs in the whole molecule?
Should be 4. Oh, H.
15. How many secondary CHs in the whole molecule? 2. I think it's 2. How many tertiary CHs in the whole molecule? 1. 1. Right there. All right, I'll draw that one in. 1. How many quaternary CHs? No such thing. Quaternary carbon don't have OH. Hopefully there's a total of 18 H's in the molecule. Is that right? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. C8, it's totally saturated, so the H's should be 18. 2 and plus 2. It's totally saturated. 15, 2 and 1, 18. Okay. By the way, the quiz. Some of you tried to determine number of H's using DUS. What I forgot to tell you about DUS, it doesn't work when you have the expanded octets in your structure. In that structure, you had a double bond to sulfur, and the sulfur then had 10 or 12 electrons around. Your DUS formulas only account for plain octets. If you start making pi bonds by expanding octets, your DUS formula doesn't account for that. Because of that, and because I didn't tell you that, but I did tell you you could use DUS to get the right number. What was the answer to that one? Number of H's, 19? 19. If you use DUS, you got 17. Okay? If anybody got 17, I'll give you the point back. Okay? Tell me at some point, and I'll give you that because you thought you could use DUS. It didn't work for that structure because the sulfur had an expanded octet. Formula doesn't know that. Okay? Anybody put 17 at some point between now and December, whatever, come by and tell me. Question?
So if you were if there was any quaternary carbons, there would be 1 in that structure.
Quaternary carbons, there's 1. 1 quaternary carbon.
But if you phrase it with a CH, a quaternary CH, it'd be
There's no such thing because that carbon doesn't have an H. Quaternary carbons never have an H. If it did, it wouldn't be quaternary.
Okay.
Because it can't have 5 bonds. Question?
Yeah, I have a question. So applying this rule of so basically primary, secondary, tertiary carbon, it's based on how many carbons they're onto. Given a mean that's like NCl2 got 1 carbon, is that considered primary amine? It's only about 1 carbon.
Chlorine and then a methyl?
Yeah, sure.
That, I reckon you still call that a primary, but
Okay.
it's usually only used when it's pretty plain hydrocarbon. It's examples like there where it gets a little iffy. And that's why this classification, as more advanced it gets, people use it a little bit different. I showed just sort of the basic, where usually it's pretty straightforward. Other questions over here, guys? Questions over here. That's what I want. If you haven't asked a question, ask a question, okay? Make the aim to ask questions. Yeah.
When naming this compound, since it has 3 methyl groups, would you have 2,2,3 trimethyl, or would you say 2,2-dimethyl?
Can you say it louder, please?
Oh, sorry. I was just asking if.
Why don't you do this? Everybody name that compound, and we'll do it real quick another day. All right? Let's move on. Okay, in terms of reactivity of alkanes, and when we get to alkenes, there'll be tons of reactivity. With alkanes, there's not much reactivity. Alkanes are pretty boring in terms of reactivity. What kind of reaction will they do? Well, the first one, combustion. That's hugely important because we heat our homes and we light our grills and stuff like that. Okay? You take butane, you can react it with oxygen in the air, all it takes is a little spark, get it going, and what's the result? All the carbons are converted to CO2, you make H2O, and you also make heat, exothermic. Okay? That's actually probably a radical oxygenation. Hard to show mechanism of how that takes place. You can balance the reaction, okay? You're going to have 4 CO2s. That's the last time you'll see me balance a reaction. Etc. It doesn't have to be, I mean, it could be bad. Probably a radical oxygenation. That's the last time we'll talk about that in organic 1 or 2. You can also do radical halogenation. React it with just a halogen, bromine, chlorine, diatomic halogen. You take this, what is that, 2-methylbutane, react it with bromine. What is H nu? Light energy, right? That's the light energy. You can do a substitution reaction. You can replace this tertiary CH with a Br. So now we're using terminology, right? And produce HBr. The tertiary H combines with the other Br, and you can get this. Mechanistically, it's a radical halogenation. We will cover this type of reaction near the end of this course. Very common radical. But that's about it for alkanes. Usually radical reactions. Not much. When we get to alkanes, we way more. Okay, we need to get through this page. I definitely want to start working some models today. All right. So on your day off on Monday, you could be working some models and stuff. Let's take a look at cycloalkanes, an important subtype of alkane. Of course, you can have various types: cyclopropane, cyclobutane, cyclohexane, etc. This was in the nomenclature. Some people say, can you have cyclopropane? Yes, you can. It's actually very common in drugs. I actually give you a sheet that shows lots of drugs with cyclopropane rings. They do have ring strain because for 9th grade geometry, this bond angle here is what? 60 degrees. Okay? Question?
Are cyclopropanes, like, are they similar to epoxy groups?
Epoxide just has an oxygen in place of one of the CH2 rings. Yeah. But that carbon doesn't want to be 60 degrees. What's the standard bond angle for such a carbon? 109.5. That carbon's sp3, right? 109.5. That's what it wants to be, 109.5, but we're making it, or nature made it, 60. Okay? It's like, I don't want to be 60. But it will be there. We call that angle strain. These two do suffer from angle strain because 9th grade geometry tells us this is what? 90. Okay? When you get up here, this is closer to 109.5, the typical and preferred. The angle strain, or stability of those guys up there, cyclopropane is less stable. Larry?
Will cyclopropene will be more flammable than regular propene because of that?
Are you saying propene?
Yeah, propane, I'm sorry.
Propane. Cyclopropene is a very unstable compound, because there you're looking for 120. In terms of flammable, I don't know, to me they're both going to be highly flammable. You'd have to get in it much more closely than I'm probably.
I'm just wondering if because it already has such a high energy state.
Well, what it will do is it'll probably give you more heat per mole. Because
Okay.
But in terms of just igniting, question?
So, why is it created in nature if it's significantly less stable?
That's a good question, but what we do know it is, it can be made. Okay? It's just important to realize and to be Yeah, it's a good question, but it can be made. You know, you could look into deeper answers to that and how the bonds are actually proposed and known to exist, because it's probably been studied very closely. And you hear things like banana bonds. Crazy names for bonds because they're very atypical. But that's a little bit beyond the scope of the course. But take a look at it. What we can say about it is the ring strain can be seen in like adhesive formation. You should be familiar with using adhesive formation from Gen Chem. The adhesive formation of the first two, which have angle strain, is actually positive. Okay? Heat of formation is the heat that's released or needed upon making the compound from the elements. In making cyclopropane from carbon and hydrogen to give that molecule, what is the delta H? For these two, it's positive. What does that mean in terms of heat needed or released? Endothermic. So what does that mean in terms of heat needed or released? You have to put heat in to make them. Why do you have to put heat in to make them? Or energy in to make them? Because you got to force these strained bonds to form. So that is seen in this. The other ones, when you make them from the elements, are actually exothermic. The ring strain can be seen from the HF. Those two have positive. Here's a take home. Your best rings are 5 and 6. Because your 5 and 6 are closer to 109.5. Now this gets a little bit convoluted. I'm not going to go all into it, but actually the big rings also suffer from strain because, pretend this is 109.5. When you go to a bigger ring, you actually have to start widening out. And that's also strain. So like an 8 and 9 member ring is actually not as good as 5 and 6. 5 and 6 are your perfect sizes. Now why is it not a positive? Well, again, it's complex. Probably because you're just making so many covalent bonds that it ends up still being exothermic. Okay. Let's look below. Let's look at some dye-substituted cyclohexanes. In this examples here, I put methyls. The methyls could be 1, 2. So if that's 1, that's 2. Or they can be in a 1-3 relationship. If that's 1, there's nothing at the 2, then that's 3. Or they can be 1-4. If that's 1, 2, 3, 4. So these are all different compounds. What's the relationship between those three? Constitutional isomers. They all have the same formula. Hopefully you can see they all have the same formula. They just have different connectivity. And that's the definition of constitutional isomers, right? So there's the idea. Different terminology is called a 1,2 isomer. Now the 1,2 isomers, we can look at it, focus in on that. And actually the 2 methyls both can be coming out. These carbons aren't tetrahedral. And so we do have what? 2 in the plane. That's in the plane, that's in the plane. 1 forward. And what? And 1 back. What's going back on this carbon? Undrawn H. Okay? Back here you also have an undrawn H. But the 2 methyls relative to each other can both be coming forward. Or you can, well that's also, well there they're both going back. Those are actually the same compound. You just take this and flip it over. Because here my thumb's coming forward, now it's going back. Okay? That's called a meso compound. At this point, this is sort of getting into test 2 when we cover stereochemistry. Important for now is when things are on the same side, it's called cis. Here the methyls are both forward. That's cis. Here the methyls are both back. It's also known as cis. On the other hand, you can have a compound like this where one methyl is forward, the other's back. Well, that's not cis. They're opposite sides, and opposite is known as trans. So both of these scenarios are trans. Later on, we'll learn these are actually different compounds. Or those are the same. So that's really getting into test 2 material. The important thing for us now is, are these constitutional isomers? Correct. Those are stereoisomers. They're not constitutional isomers. They have the same connectivity. You have a methyl connected here and here. 1 and 2. Methyl connected 1 and 2. If you name this compound, what would be the name? 1,2-dimethyl cyclohexane. Stereochemical descriptor. What would be the name of this one? 1,2-dimethyl cyclohexane. Same thing. If you have the same name, you're not constitutional isomers. Constitutional isomers have different names. These are both trans, but they are different compounds because this requires a second stereochemical descriptor in front of it. We'll learn that during test 2 material. Important thing for now is to know that they're not constitutional isomers. That's the important thing now. And the other type is stereo.
And you just say the stereo have the same name.
Stereoisomers have the same name, they just differ by some descriptor in the front, like cis or trans,
Okay.
or RS, or E or Z. We'll learn all those.
This is what's going on with, I think it's sucrose or glucose, isn't it? One's alpha, the other one's beta.
Alpha and beta are stereoisomers. That's a stereochemical descriptor, the alpha and the beta. Trans fats have, well, that's alkenes. This is a different type of trans, but they're opposite on the alkene. Trans means the same thing.
So are those meso compounds too?
No, these are meso, they're the same. Those are not meso compounds, they're different. That's test 2 material though. There are some drugs with cyclopropanes. I'm actually interested in trying to write a paper about all the drugs that have cyclopropanes because there's so many. That's actually a cyclobutane there, but up there. Nowhere in the literature has anybody ever kind of stressed this and sort of categorized them and did a table. If anybody's interested in trying to do something like that, to get a publication, let me know. Actually, look at the structure on the workbook. Oh, I don't know why I didn't. Usually I'd put cyclopropanes on there. That one's got a cyclobutane though. It's also got a big, like 7 or 8 membered ring. Question?
When cyclopropane has covalent bonds to other carbons, does it make it more stable or is it still unstable?
When it has what type of bond?
When it has covalent bonds to other carbons, does it make it more stable or is it still unstable?
It's not a big answer. I mean, it's going to vary slightly. I'm not sure if you're getting at something that you've read, but it's not really relevant. Question?
I have a question regarding alkane nomenclature. So let's say you have like 3 methyl groups like as substituents, but 2 of them are located on like a separate carbon. So would that be trimethyl, and then you have to indicate like where the dimethyl is?
No, you just call it like 3,3,6 trimethyl.
That answers my question.
2 of the methyls are on the 3, and the other one's on the 6. Okay, we need to get into conformations. Important with alkanes, they don't do a lot of reactivity, but the conformations is important. Start doing that. We also have our blue handout. Everybody got the blue handout? Okay, here's ethane. Many ways to draw an organic compound. Here it is, sort of all the bonds drawn out, and the tetrahedral nature. Two in the plane, one forward, one back. Okay? Very descriptive drawing. We're going to look at these. You can look at them straight on. We'll also very often look at them from the side. Like here's your eye, and I'm looking sort of down this bond. Okay? That's ethane. I can sort of make ethane. I'll do it like this. Okay, here's your two carbons. Then these, instead of these being methyls, these on the ends coming out for H's. So there's a carbon with 3 H's coming out. Carbon with 3 H's. Now you can look at this. This is drawn here. Let's see. This H is in the plane, straight up in the plane. Pretend like this is the board. Over here, this H is in the plane, but it's down, so that's like this. Then on this carbon, you got an H coming forward. You see how it's bolded coming forward? And then one going sort of up and back. Over here, I've got, if I'm looking at it here, I see an H going straight up. Okay? And then I also see an H coming towards you guys. It's the bold one coming out. See, this is me here. And I got an H going behind the board. So that's that. Now, we'll have to maybe draw it like this. Sawhorse structure, you don't see these too much anymore. I don't know why. Sort of like that. That's where it's sort of like this. This you have to sort of know that this is not all planar. Back one going straight down. If that one's up, these two are actually out of the plane forward and back. But the sawhorse doesn't really show that. That's another way. So you have to know that there's truly tetrahedral nature here. That's called a sawhorse structure. When you see those, you should take a minute and kind of work with it a little bit, see what they're saying in the book. The 3D form is also called a perspective drawing because we see the perspective, the stereochemical perspective of things going certain ways. It's just terminology. I put this all here because it's just different ways to look at it. Okay. This is kind of a ball and stick form of representation. You see that sometimes instead of just simple line bond. So maybe refer back to that type of stuff. This progression here is basically taking it from drawing it like this to actually drawing what you see if you're looking from the side. Okay? I'm looking from the side, like up there. How do you draw what I see on the board? Well, we're going to actually draw it like that. We're going to have to learn how to do that. All right? But that's it there. This is Newman projection. Newman was a chemist at Ohio State back in like the 60s and 70s. Passed away now. Actually, I worked with someone who worked with Newman. Said he was quite a character. He said, don't repeat this. He said he would wash his coffee cup out with the same brush he washed his flask out with. Me too. I don't see the problem with it, as long as you're not working with I mean, you know. He also said Newman was very big on melting points. Every time you say, well, did you get melting point? How was your melting group? Okay. Well, Newman also developed these representations for a way to show the compound. Called a Newman projection now. I call it circle, circle, dot, dot. Remember that? Because that's how we'll get to draw it. We'll see things like dihedral angle. The dihedral angle is the angle between H's. We really need to wait before we describe this, but we'll do that. things on down. Okay. Let's move away from there and let's look at this. Some terminology. First off, here's that thing. This is a sigma bond. It can rotate. See, this over here can just turn. Well, since it can turn, we can say these could be like this, or that could be like that. Or if we mark these somehow, they could be like that or like that. Well, first off, what do you call this? What do you call that? What do you call that? And also, which is preferred? Those are the things we're going to be looking at. As you rotate this thing, each different possibility of the relative that to that is called a conformation, or a conformer, sometimes called a rotamer. And what we'll say is which conformation is preferred. I mean, is it going to mainly be like that, or is it going to be like this? Okay? Now, if it was like this, what can we call this? This might be better. Let me really note that these are the ones we talked about by putting blue ones here. Okay? I mark the H's or these are methyls. It can be like that or like this. What do you want to call that conformation? Give me a name. One word. I mean, you could say the blues are beside each other, but we need a one-word name. Cis? That's not bad, but it's not used here. And we can say why later. If I look through here, I can't see the one behind it because the front one's blocking it. It's kind of like the sun blocking the moon. Eclipsed. This is eclipsed. Okay? I can't see the one behind it because the front one's blocking it. It's eclipsed. Now, what if we have this? Pair is it's not right here, but I see what you mean. Anti? Yeah. Anti? They're kind of opposite. Trans we use, but here we use anti as the term. What about if it was just turned a little bit like this? Is that eclipsed? No. No longer. What is that? It's gouache, but gouache is a type of what? Does it say staggered? Yes. It's staggered. That's staggered, but it also is gouache. Okay? Probably on the next page. It's probably not written on there. Let's see. Let me look at the. Let's look at the dihedral thing while we've got some time. When you're eclipsed, the dihedral angle is 0. The dihedral angle is not the angle between two things on the same carbon, but the angle between something on this carbon and another one. That is this versus this. There it's 0. If I turn this here, right there, that one's straight up and this one's. What's the dihedral angle between the two blues? 90 degrees. See that? It's a 90-degree dihedral angle between the blues. What if it's here? It's 180 dihedral angle. Okay? That's the dihedral angle. Should be in your textbook. So the anti has a 180 dihedral angle. Okay? Question?
Say, like, when you just went to 180, but if you go further, are we going to go in one direction, like clockwise, or will we have to go counterclockwise?
It doesn't matter. Dihedral angle, though, would not go beyond 180 because now you're actually getting less and less, and you're going back to 0. Okay? Let me see if there's anything else to mention now, because what you need to do is you need to be doing some preliminary work on this, because on Tuesday we're going to hit all this stuff. You need to be prepared with your questions. Okay? Be prepared to. Let me just see. Give me a second here. Just a second. We'll look at the different energies as you rotate around. Which is better? But we'll be naming them as we go around. You need to be able to sort of graph that, okay, type of thing. But then we will move on to it's not here. Cyclohexanes, very important. On the blue, there's lots of problems to be working. Use that as your study guide between now and Tuesday. Let's be prepared to work these problems on Tuesday. Have a safe weekend, guys. Some of you still have labs today, tonight, and tomorrow.